If the data in a stream is arriving too rapidly, we may not want to or need to look at every stream element. Perhaps we can get by with just a small sample of the values in the stream. But we have to worry about two things. First, the sample better be unbiased. But second, the sampling process must preserve the answer to the query or queries we want to ask about the data. Unbiased sampling is not hard, but carelessly choosing how we sample can distort the results of queries. So after a discussion of the pitfalls, we'll see a method that preserves the answer to a given query, introducing only the noise that comes from the fact that we're sampling at random. Let's take up an example. Google has a stream of search queries coming in at all times. We might want to know what fraction of search queries received over a period, such as a month, are unique. That is, there's only one occurrence of that search query in the entire month. Many questions about the stream can be answered by sampling the stream. Suppose, to be concrete, that we randomly select 1/10 of the queries to be examined. For example, if we wanted to know what fraction of the search queries were single-word queries, we could compute that fraction for the sample and be pretty sure that it was very close to the fraction for the stream as a whole. That is, over a month, a 1/10 sample would be 1 billion queries or more. Statistically, if those queries are selected at random, the deviation from the true answer will be minuscule. However, we want the fraction of unique queries, and this query cannot be answered correctly from a random sample of the stream. In fact, as we shall see on the next slide, there's not enough information to deduce the fraction for the entire stream from the fraction for the sample. Let's do the math for the matter of unique queries. First, we know that there will be, in the sample, very close to 10% of the query occurrences of the original stream. The problem is that the probability of a given query appearing to be unique in the sample gets distorted because of the sample. First, suppose the query is unique in the stream as a whole. It has a 1/10 chance of being selected for the sample. That's fine. It says that the fraction of truly unique queries that make it into the sample is the same as for the whole stream. If we could only count the truly unique queries in the sample, we would get the right answer. However, suppose a search query appears exactly twice in the whole stream. The chance that the first occurrence will be selected for the sample is 10%, and the chance that the second occurrence will not be selected is 90%. Multiply those, and we have a 9% chance of this query occurrence being unique in the sample. Moreover, the first occurrence could not be selected, but the second is selected, and that's another 9% chance of a query that really occurs twice, looking unique in the sample. That's a total of 18%. I'll let you do the calculation, but a query that appears in the stream 3 times has a 24.3% chance of looking unique in the sample. And in fact, any query, no matter how many times it appears in the original stream, has at least a small chance of looking unique in the sample. So when we count the number of unique queries in the sample, it will be an overestimate of the true fraction of unique queries, very possibly a substantial overestimate. In fact, there could be no unique queries in the original and yet many in the sample. And worst, we just don't know from the sample whether we're looking at truly unique queries or not. We may as well toss out the data and start over again. If you think about it, the problem was that we assumed we flipped a 10-sided coin every time a new element arrived on the stream. The consequence is that when a query occurs at several positions in the stream, we decided independently whether or not to add each one to the sample. That isn't what we want. We want to pick 1/10 of the search queries, not 1/10 of the instances of search queries in the stream. And we can make the random decision the first time we see each search query. If we kept a table of our decision for each search query we've ever seen, then each time a query appears, we could look it up in the table. If we found we do the same thing we did with the first occurrence of that query, add it to the sample or not. But if we didn't find the query in the table, we flip that 10-sided coin to decide what to do with it and record the query and the outcome in the table. That's kind of unappetizing. It will be hard to manage the table, and there is a lookup with each stream element. Fortunately, there's a much simpler way to get the same effect without storing anything. Okay, let's pick a hash function from search queries to 10 buckets, 0 through 9. When a search query arrives, hash it. If it goes to bucket 0, then add it to the sample, and if it goes to any of the 9 other buckets, do not add it to the sample. The cool thing about this approach is that all occurrences of the same query hash to the same bucket because the same hash function is always applied. As a result, we don't need to know whether the search query that just arrived has been seen before, and we don't need to know what action we took. We can be sure that if it did appear before, we'll do the same thing now that we did then. The result of sampling in this way is that 1/10 of the queries are selected for the sample. If selected, then the query appears in the sample exactly as many times as it does in the stream as a whole. Thus, the fraction of unique queries in the sample should be exactly as it is for the whole. Suppose now that we want our sample to be not a fixed fraction of the total stream, but a fixed number of samples from the stream. What we can do is hash to a large number of buckets and accept for the sample not just one bucket, but enough buckets that the resulting sample just stays within the size limit. If, as more stream elements come in, our sample gets too large, we pick one of the buckets that we had been including in the sample. We delete from the sample just those elements that hash to that bucket. Organizing the sample itself by bucket can make this decision process efficient. I won't go into the details. So let's rethink the example we've been working with. We still want a 10% sample of the search queries, but we realize that eventually even the 10% sample will get too large. So we want the ability to throw out of the sample some fraction of its members. And of course, we want to do it consistently so that if one occurrence of a query is tossed, then all occurrences of that same query are tossed. Hashing to 10 buckets is fine to get a 10% sample, but we need to be prepared to deal with smaller fractions, so we need to hash to many more buckets. We'll pick 100 buckets for our example, but it could be 1,000,000 buckets or even more. As long as we're happy with a 10% sample, then we'll accept for the sample those elements that hash to 10% of the buckets. We could choose any 10, but let's choose 0 through 9 to be specific. Now, suppose we're going along and at some point the sample size gets too big. So we pick one of the buckets to get rid of, say bucket 9. That is, we delete from the sample all those elements that hash to 9 while retaining those that hash to 0 through 8. Implementation is simple if we store the sample by bucket. We just return bucket 9 to available space. Now our sample is 9% of the stream. In the future, we only add to the sample new stream elements that hash to 0 through 8. Now, sooner or later, even the 9% sample will exceed our space bound, so we get rid of those elements that hash to 8, and then 7, and so on. If eventually even a 1% sample is too much, we're stuck, but then we should have taken the opportunity to hash to more buckets than 100, probably lots more. The idea we explained by example is really an instance of a general idea. We can see any form of data as key-value pairs. Okay, we can choose our sample by picking a random key set of the desired size and taking all key-value pairs whose key falls into the accepted set, regardless of the associated value. In our example of search queries, the search query itself was the key and the value was null. It was not really there. In general, we select our sample by hashing keys only. The value is not part of the argument of the hash function. We pick an appropriate number of buckets for acceptance, and we add to our sample each key-value pair whose key hashes to one side of to one of the accepting buckets. So let's look at a simple example where picking the right key makes all the difference. Imagine our data elements are tuples with 3 components, an ID for some employee, the department that employee works for, and the salary of that employee. For each department, there is a salary range, the difference between the maximum and minimum salaries taken over all the employees of that department. Again, let's suppose we want to use a 10% sample of those tuples to estimate the average salary range. Picking 10% of the tuples at random won't work. For a given department, we're likely to be missing one or both of the employees with the minimum or maximum salary in that department. Thus, the differences between the max and min salaries in the sample for a department is likely to be too low. That is, we have introduced a bias toward the low side by our poor sampling strategy. The right way to sample is to treat only the department component of tuples as the key, and the other two components, the employee ID and salary, as each part of the value. In general, both the key and value parts can consist of many components. If we sample this way, what we're doing is sampling a subset of the departments, but for each department in the sample, we get all its employee salary data, and we can get the true salary range for that department. When we compute the average of the ranges, we might be off a little because we're sampling the ranges for some departments rather than averaging the ranges for all departments. But that error is just random noise introduced by the sampling process, not a bias in one direction or another.